Okay, let's go right away into our example problems for Thevenin and Norton. Does anyone have any questions before I begin? Okay, section 02, example 2. Find the Thevenin and Norton equivalent circuits if the 2-ohm resistor represents the load resistance. So I would like all of you to get your calculators out. We'll solve this together. And what I want you to do is, let's see, menu share. Okay, slide should be visible now to everyone. Okay, all right, what I want you to do is to draw out the circuit first to determine the Thevenin resistance. But first, look at the problem statement. What is it telling you? It is telling you that the 2-ohm resistor represents the load resistance. Okay, so what is the first thing that we have to do? We have to set up the problem, right? In the setting up the problem, if the 2-ohm resistor represents the load resistor, it is the same as stating determine the Thevenin and Norton circuits as seen by the 2-ohm resistor. So we remove the 2-ohm resistor from our analysis, right? So the circuit that we will analyze does not include the 2-ohm resistor. Okay, so then the circuit looks like this. You have to establish the terminals where you will analyze the circuit. And so once the 2-ohm resistor is removed, the terminals where it was connected are now left open. A and B is already noted in the problem itself in the circuit diagram. If it's not, you label the terminals whatever you want. X and Y, 1 and 2, doesn't really matter, but at least make a notation, right? So these are the terminals where you will analyze the circuit. Okay. So now draw out the circuit to determine the Thevenin resistance between A and B. What do we do? Take it one step at a time. The first step is to determine Thevenin resistance. We reduce all the independent sources to 0. Reducing the source to 0 means you replace all the sources with either a short circuit wire or an open circuit. Voltage sources are short circuit. The only thing we have here is a voltage source. And so you replace that with a wire and you redraw the circuit. Redraw the same circuit, except in place of the voltage source, now you have a wire. Then look at it for 15 to 20 seconds. And let me know what you think about finding Req. Students who are online, I hope you're doing the same work. RTH is Req. A, B, REQ between A and B. So does everyone have the same answer? Any questions? Now, of course, this circuit is rather simple in the sense that it only has one source, right? Next example has two, and then circuits you may see in real life have multiple sources, but the concept remains the same. Everywhere you see a voltage source, you replace with a wire. Everywhere you see a current source, simply replace with an open circuit. Basically, take it out of the circuit. So what do we see? What answers do you have for REQ? Okay, one student says 8 ohms. 8 ohms, there's a nod, there's a thumbs up. 2 thumbs up. Take your time and verify. Online students, what answers have you obtained? REQ, starting at the farthest end, we see 12 is now connected to 6, right? Because it's in parallel. 12 is connected to 6, so it is in parallel, plus 4 in series. Thus, you end up with 8 ohms. Thevenin resistance RTH is equal to REQ, which is 8 ohms. Any questions? Okay, next step, find Thevenin, either find Thevenin voltage or find Norton current. Doesn't really matter which one. We are required to find all of them, all three quantities. So let's take Thevenin voltage next and draw out the circuit that is required to analyze for Thevenin voltage. Everything that we did for Thevenin resistance stays in that analysis. We do not take anything from there. We do not take the circuit. We do not take the analysis or the resulting values, right? The Thevenin resistance circuit or the Thevenin resistance value has no bearing whatsoever to determine Thevenin voltage. So to determine Thevenin voltage, you go back to the original circuit. The original circuit or the circuit that you need to analyze is here. Okay. So to determine Thevenin voltage, all you're going to do is we're going to draw out the same circuit as it is. So in the exam or in the quiz, if I ask you, draw the circuit that is required to determine Thevenin voltage, this is the step. Okay. You're going to draw out the original circuit with the terminals of analysis A and B. Then note the voltage polarity and VOC, the open circuit voltage that you will be analyzing for. 30 volts, 6 ohms, 12 ohms, 4 ohms. That's it. This is the circuit we need to analyze for Thevenin voltage. There's essentially no modification. We need to keep the terminals open, right? So if we removed the 2 ohm resistor from our analysis, the rest of the circuit stays as it is. There is no shorting out of the voltage source, no removal of any current sources. You take the entire circuit as it is. If you remove any component, from here right now, then your circuit is incorrect. The rest of the analysis wouldn't matter. So this is the absolute most important step. Your circuit setup should be correct. The circuit is, again, rather straightforward and simple, and so it doesn't cause any issues. You simply draw it out. So now you analyze this circuit to determine the voltage between A and B. You're essentially trying to find VAB, voltage at A measured with reference to B. That is your open circuit voltage, according to the polarity that we have set. What techniques come to mind? Node voltage analysis, absolutely. Mesh current analysis. Superposition, there is no need for superposition. You only have one source. You can also do series parallel analysis. I can tell you it's a one-step answer with one equation. I like to use this as a teaching moment. So, what is the relationship between 12 and 4 ohms? One answer says series. How about 4 and 6? Series, parallel. Think about this. For two resistors to be in parallel, both ends have to be connected together. Any of the three resistors, are they connected with their both terminals together? No. They're connected together at that center node right here. That center node, right? But the other end of those resistors are not connected together. So they are not in parallel. Then, in order for two resistors to be in series, they have to be connected at one junction, but the junction should not have more than two connections. So, if you look at that center node, how many connections do we see? Are they in series? Who says yes and who says no? I'll tell you the correct answer is yes. They are in series. But which two resistors am I talking about? 12 and 6, yes. But why? Absolutely. So if we take a look at the circuit, let's say the voltage source is supplying some current, right? It goes around, goes to the 12 ohm, and we would think that it would split between 4 and 6. But if it goes down 4, it's a dead-end street. Current needs a closed pathway to flow through. If it's a dead-end street, no traffic is going to go that way. No current is going to flow that way because it is an open circuit. So the 4 ohm resistor may as well not be connected or not be part of the circuit at all. But here's the important thing. Because there is no current flowing through the 4 ohm resistor, essentially the voltage at both ends of that 4 ohm resistor is exactly the same. So the voltage at this open terminal A is the same as this node right here, and I'll call this node as C. I think I figuratively saw a light bulb go off or go on. Go ahead. Sorry, what? No, it doesn't. The question being asked if the current goes through the 4, no, it doesn't. It doesn't go through the 4 at all. Is that what you were asking? There would not be a measurable voltage. No. If you measure the voltage across 4, the answer would be 0 volts because we are measuring across 4. Essentially, whatever the voltage is you measured at node C is the same voltage you would measure at node A. No current flows through. Again, voltage is the difference in electric potential. So potentially, current can flow if there is a closed pathway for the current to flow through. But there's no current flowing, so there is no voltage drop. Because there is no voltage drop, the potential stays the same. So very simple circuit essentially, but a very important concept. That's why I wanted students to think this through. Okay. If a terminal or a component is connected only at one end and the other end is left free and it's not connected to anything, it is an open circuit, it may as well not be part of the circuit at all. And this is the reason why. Okay. So take it logically, step by step. Do not rush through things. Okay. Simple circuit. And as I promised, one-step answer. If I redraw the circuit, I established that 12 and 6 are in series, right? 12 and 6 are in series. So I can draw the circuit this way too, just to visualize it in an easier manner. Exactly same circuit. I'm just drawing both resistors vertically. And then from this node C, I have the 4 ohm resistor coming out, terminal A. This is terminal B. Take your time and look over the circuit. So again, in the exam or in the quiz, redraw the circuit as many times as you need until it starts making sense. Okay? It doesn't take long. You might think it takes long, but it won't take you more than a few seconds to do that. So we have a 12 ohm resistor, we have a 6 ohm resistor, and we have 30 volts. 1 voltage applied to a series connection of resistors. What technique comes to mind? What happens to current in a series connection? It stays the same. What happens to voltage? Voltage gets divided or split. Voltage divided voltage division. You can apply voltage division. Or you can take it 2 steps. You apply Ohm's law, find Req for the 2, right? Find current, and then find voltage, either ways. The important point or the important concept was that VAB, the voltage at A measured with reference to B, is the same as the voltage at C measured with reference to B. VAB is equal to VCB. Okay, VAB is equal to VCB. And VCB can be given using voltage division 30 times 6 divided by 12 plus 6, which is 18. And so the answer for this is 10 volts. VTH is equal to the open circuit voltage, which is VAB, which is 10 volts. Don't need an oval. All right, think on this. Let me know if you have questions. Again, you're not learning a new technique. The techniques you have already learned and the concepts that you have learned, you need to take all of it together now and see how you can apply it to solve a problem. Any questions come to mind? No questions? All right. Yes, go ahead. Yes. The question being asked is, if you solve for the voltage across the 6 ohm resistor, then that's the same as the node voltage at C. Yes, the answer is yes, because the 6 ohm is connected between C and B. Yes, good question. Good question. We can, again, we can state that VAB is VCB because B is the common node for everything. B is where we are measuring Thevenin voltage. B is where the 6 ohm resistor is connected. B is also where the power supply voltage is connected. And because the circuit connection is, B is common to that circuit connection, that's why we can apply voltage division and solve it. In a different circuit, the connection might be different, then we would use a different technique. Shall we move on? All right. You move on and you draw the circuit for Norton current, or to determine Norton current. leave this behind because this circuit has no bearing on the determination from Norton current. From Norton current, you go back to the original circuit, and this time, again, current needs a pathway to flow through, so you place a short circuit wire between the output terminals, right? So you draw the exact same circuit with the terminals A and B, and you place a wire between A and B for the current to flow through. Okay, let's go ahead and draw that out. We have A, we have B, place a wire between them. Arrow should be pointing downwards. That's our assumed direction. $12, $4, and $6. And let's keep this as C. This is 30 volts. They all have the exact same circuit. Okay, so what do we see? How can we begin analysis on this one? You can, again, do series parallel analysis, node voltage, mesh current, any technique that comes to mind. There are multiple ways to solve it. Every quarter, I solve it in different ways. There's like 3 or 4 different ways you can solve this. Now, is this first question, is this circuit the same as the one we use for Thevenin resistance? No, because Thevenin resistance doesn't have any sources. How about Thevenin voltage? No, because there is no wire between A and B. The reason I'm emphasizing this is because every quarter I do see students who are not, or who make errors in trying to set up the problem itself. And so I always want to take it slow and ensure that students are following along, okay, the work. So again, Norton current requires a wire to be placed at the terminals of analysis. When you place a wire, that circuit is different from the Thevenin resistance and the Thevenin voltage. Okay, it also has sources and the extra wire at the terminals. Circuit has now changed. What do we see? Because of the wire, the 4 ohm resistor is now in contact with the 6 ohm resistor. It was already in contact at one end on the left side. Now it's also connected on the right side. So both terminals of 4 and 6 are connected together. So they are in parallel, right? Both ends of the resistors 6 and 4 ohms are connected together. So they are in parallel. The relationship between the 12 ohms and the rest has not changed. That remains the same. But if we combine 4 and 6 together in parallel, we can state that the 12 ohm is in series with the other two. And so let's draw out that series connection. So I would have the 12 ohm, and then I have the 4 and the 6 ohm resistor. Now, when we redraw the circuit like this, you keep the nodes in mind. So this is my 12 ohm resistor, this is the 6 ohm, and this is the 4 ohm, okay? If you follow the path for ISC, the short circuit current, where is it coming from? Look at the first diagram. Where is ISC coming from? Or which component is it coming from? Which component is it flowing through? Everyone is trying to hide their eyes and avoid making eye contact. It's not a verbal quiz. I want to ensure that students are looking at it and understand this. So I'm asking you the questions, and hopefully you will train your brains to think in the same way and ask yourself the same questions when you're trying to solve these problems. So if you want to look at ISC, the short circuit current, you want to look at which components that that current is flowing through. So if we take ISC back, we extend it back as I did here, which component is it flowing through? The 4 ohm resistor. So we need to find the current that is flowing through the 4 ohm resistor. And so these are the questions you should be asking yourself when you're trying to solve these problems, right? Because the open circuit voltage, the Thevenin voltage, as well as the Norton current would be for a specific component. If you find that component, that's all you need. So the 4 ohm resistor current is ISC. So I mark it there. And then I have the total current. I call this IT. This is 30 volts. To find the current, the 4 ohm resistor, what techniques come to mind? You can do series parallel analysis, find the total current, then perform current division. You can find the voltage across the 6 and 4 ohm resistor, and then apply Ohm's law again, essentially the same technique, right? You find the total Req in the circuit, find the total current IT, and then find the voltage across 6 and 4 ohm resistor. Again, this is something that you've already done before, right? Series parallel analysis. Homework number 7. Something, yeah. Okay, so let's see. 6 and 4 in parallel. 6 4s are 24 divided by 10 gives me 2.4 ohms, right? I can apply, let's see. Well, we can do the same thing we did earlier. We have 2 resistors in series, 12 ohms and 2.4 ohms. Does everyone see that? 12 and 2.4. Then apply voltage division, find the voltage across that 2.4 ohm combination. So from voltage division, I can state that, let's see, let's call this Vx. Vx is equal to 30 times 2.4 divided by 14.4. And that gives me 5 volts. One 1.25. 1.25. You can also solve this by finding IT and applying current division. Again, multiple ways to solve the same. All right, any questions? Does it make sense? Right. All right, let's pick up the pace a little bit. Verify your answers by applying Ohm's law. VTH should equal IN times RTH. IN is 1.25 amps. RTH was 8 ohms. And that gives me 10 volts. The answer is verified. Yes. Good question. I'll repeat it. Question is, why can't we use Ohm's law to find Norton current? The answer is sometimes there are, well, not sometimes, oftentimes the circuits that we see in real life, the resistance is not reducible. So we cannot find Thevenin resistance directly. Those are the times you would actually need to find the Thevenin voltage and the Norton current, and then use Ohm's law to find RTH. So real life circuits are far more complex. Oh, what happened here? Are far more complex. And so it is not possible to reduce those circuits or those resistances down to one single resistor. Also, many of the electronic devices that we use in electronic circuits, like transistors, for instance, they're modeled with dependent sources, the diamond ones. And those sources cannot be reduced to zero. So if you have those kind of sources in your circuit, you can't find Thevenin resistance directly. Those are the two reasons. So again, it's also a skill that students need to have. Obviously, again, going back to the first day of class, this is a non-E major class, so we don't go too in-depth, right? We don't go scuba diving, we're just snorkeling. So it's hard for me without actually showing complex problems on, where it would be applied. But if you take, let's say, EE 321 electronics, where you model transistors using a dependent source, so there's a dependent source in there. If you have a circuit with a dependent source, you cannot reduce it to one single resistance. Okay, let's see. Then finally, the final circuits would look like this. Final Thevenin circuit would simply be the voltage source, the Thevenin voltage with a Thevenin resistance, and the 2 ohm resistor connected back into the circuit. This would be RTH, which is 8 ohms, and this would be VTH, which is 10 volts. And the final Norton circuit, this is something I will ask in the final exam. Ohms IN is 1.25 amps. Yes. The original circuit where it stated, find the Thevenin and Norton if the 2 ohm resistor represents the load network. Okay, 15 minutes left. Let's go ahead and solve example 3. Similar problem statement, find the Thevenin and Norton circuits if the 17 ohm resistor represents the load resistance. So Thevenin resistance requires us to remove the load resistor and all the sources. So I'll jump in right away. Draw out the circuit without the sources. And 17 ohm resistor is now removed. So it's A and B, and REQ between A and B is my Thevenin resistance. Now, wherever there are sources present, you replace with a short circuit or an open circuit. Voltage source is connected with a wire. And so I'm going to simply place a short right there. And the current source at the top, the 1.5 amp current source, is replaced with an open circuit. You don't need to draw that out. Open circuit means just an empty spot. So that one is gone. The only thing left are the 3 resistors. It becomes kind of a simple circuit. Starting at the far end, you have 5 in parallel with 20, which is then in series with 10. And that gives me 14 ohms. So RTH is equal to REQ, 14 ohms. Again, I directly drew out the circuit, but for every circuit, 17 ohm resistor is not part of the analysis. All right, questions? Any questions at all? Yes. Yep. Not really, no. The question being asked is this circuit kind of becomes similar to the previous one because we removed the sources. And the answer is no. It's just the chosen examples that it's just a coincidence. But the circuits that you might see in the quiz or in the final exam would be very different. Okay, Thevenin voltage. Let's see. Thevenin voltage, you draw out the circuit exactly as it is with the component removed. Terminals A and B are open, and you analyze the circuit between those terminals to find the open circuit voltage. Hmm. 10 ohms, 20 ohms, 20 volts. Plus minus. So this is A, this is B, and VOC is measured between those terminals, 20 ohms and 10 ohms. 20 volts. Okay, so what technique comes to mind? We can use voltage division, but there are two sources in there. We can do mesh current analysis, absolutely. We can do node voltage analysis. We can do superposition. I've done superposition in the past. Superposition, of course, would take longer because there are two sources, so you have to analyze it twice. If I count the number of nodes, I can see that there are 1, 2, 3, 4 nodes. 1, 2, 3, and 4. Yes, 4 nodes. So there's A and B, of course. There's a node in the middle, a node in the far left, C, and this is D. Meshes, there are only 2 meshes in there. So you could apply mesh current analysis, or whether you apply node voltage or mesh current, both cases you would only have 2 unknown variables. For node voltage, we have A, B, C, D, 4 nodes. But if we choose B as a reference, if B is a reference, then VB is 0 volts. And also VC is 20 volts. The 2 unknowns left are A and C. Sorry, A and D. A and D. If you apply mesh current analysis, you have 2 mesh currents, still 2 equations. Node voltage analysis, 2 unknown variables, still 2 equations. So you can take your pick, whichever one you wish to, whichever method you wish to use. Either one is fine. In this case, A and D are not the same because you have the 1.5 amp current source flowing through it. Okay, so it's not the same. So let's see. Let's do, since I marked this out, let's do node voltage analysis. Again, as I said, I have done superposition in the past with this. Let's see, mesh current 16. Okay, VOC is VAB. O is 16. Yeah, I'm gonna move a little faster. Node voltage analysis, mark of the branch currents. Okay, so let's call this I1. I1 flows from the voltage source. It is also flowing through the 5 ohm resistor. I2 is the current flowing to the 20 ohm resistor, and let's call this I3. That is flowing to the 10 ohm resistor. Again, node voltage analysis requires us to write KCL. To write KCL, we need to assign branch currents along with direction. Logical assumptions, I1 should be flowing up when it goes towards the right through the 5 ohm resistor, hits the junction, and I2 should be going down. It doesn't matter which direction you assume. These are the directions I assumed. You can choose something else. It'll still work out the same. But if you look at I3, what can we see? I3 is coming directly from the 1.5 amp current source. So I can assume that as my current. I3 is the current that is coming from the 1.5 amp source. If you apply KCL at A, one current coming in, one current leaving, I3 is 1.5 amps. Now you apply KCL at D. So this is KCL at A. You apply KCL at D, and you have 4 currents. Actually, yeah, 4 currents. You have I1 coming in, you have I3 coming in, and you have 1.5 amps leaving, and you have I2 leaving. Right? Currents entering the junction equal to currents leaving the junction. So I1 and I3 coming in, and 1.5 and I2 leaving. But we establish I3 is 1.5. So they cancel each other out. And so all I get is I1 minus I2 is equal to 0. Or I can write I1 equals I2. That would be far easier. Now you apply Ohm's law and you express each current in terms of the resistor voltages. So I1 would be voltage across the 5 ohm resistor. And because current is flowing from left to right, node C is higher than node D. For I2, it's flowing from top to bottom. So node D is higher than node B. And we solve this equation, VC minus VD. We already established VB is 0 and VC is 20 volts. And so I get, what do I get? 5 times 20, 4 times VC minus 4 times VD is equal to VD. Therefore, 5 times VD is equal to 4 times 20 is 80. For VD is 16 volts. But I still need to find VA. Find VA, I'm going to use I3. I3 can be written as VA minus VD. It's the current flowing through the, what resistor is it? 10 ohm resistor. Because of our assumed direction, A is higher than D, so it's VA minus VD. Plug in all the known values and solve for VA. (15 plus 16 gives me 31. 31 volts. We're almost out of time, so if you have to leave, go ahead and leave. I'll keep on recording for IN, and then you can look at that video later for the last portion. So VA is 31 volts. VTH is equal to VOC, which is equal to VAB, 31 volts. For Norton current, IN, the circuit should look like this. Plus minus. And then 1.5 amp current source. And a short circuit wire at the far end between A and B. This is 1.5 amps. This is 5 ohms, 10 ohms, and 20 ohms. So let's use mesh current analysis this time. And if I choose mesh current analysis, I'm going to label this as M1, M2, and M3. Call this I1, I2, and I3. All of them are in the clockwise direction. Right off the bat, I can see ISC is the same as the mesh current I2. So I can define ISC as the mesh current I2. Also, I can assign a value for the mesh current I3 as 1.5 amps. So only two unknowns in the circuit. There are two unknowns. I need at least two equations. Let's apply KVL in mesh 1. KVL in mesh 1 gives me minus 20 plus 5 times I1 plus 20 times I1 minus I2 equal to 0. So 25 I1 minus 20 times I2 is equal to 20. You reduce that, you get 5 times I1 minus 4 times I2 is equal to 4. Call this equation 1. And then you apply KVL in mesh 2. And I obtain 20 times I1 minus I2. Oh, sorry, we are in mesh 2. So I2 is positive. So I2 minus I1 plus 10 times I2 minus I3. Again, we are in mesh 2. So I2 is positive. The outside currents are negative. This is equal to 0. You solve this and you obtain 20 times I2 minus 20 times I1 plus 10 times I2 minus 10 times I3 equals to 0. Reduce that, you get minus 20 times I1 plus 30 times I2 is equal to 15. Label this as equation 2. solve these equations using any method you choose, MATLAB, programmable calculator, or manually. If I solve this manually, I can do, let's see, equation 1 times 4 gives me 20 times I1 minus 16 times I2 is equal to 16. Let's move this to the left a little bit. Okay. I'll call this equation 3. So equation 2 plus equation 3 gives me, what does it be? 14 times I2 is equal to 31. Therefore, I2 is equal to 2.2142 amps. And because that is my mesh current, I can directly write IN is the short circuit current ISC, which is equal to the mesh current I2, which is 2.2142 amps. And that's it. The final Thevenin circuit will be exactly the same as example 2. You simply draw out the voltage source and the current source, and you plug in the 17 ohm resistor back into the circuit. To verify your answer, VTH should be equal to IN times RTH. It's 2.2142 times 14 gives you approximately equal to 31 volts. So verified. Okay, sorry about going over time today. We'll see you all in next class. Again, the homework is due, I believe, tomorrow. If students have any issues, reach out to me. And otherwise, I'll see you all on Friday.